Here we have our last little video for section 4.2 on linear combinations. We just want to talk about this last theorem and see a couple quick examples, or at least motivate how you might proceed through those examples. So this theorem, let's start at the beginning, says let v1 through vm be vectors in a vector space V. Now let U be the set of all linear combinations of that v1 through vm set of vectors. All right, so any combination of these guys, we're going to say that's an element of U. U is the set of all those. With that definition of U, we can say U is a subspace of V spanned by these vectors v1 through vm. All right, that makes sense from how we defined what it meant for vectors to span a space. But now we're going to say a little more. We're going to say U is said to be the vector space generated by that set of vectors v1 through vm, and U is usually denoted as span of that set. Right, so here we're kind of thinking of span as being more of a noun. Right, this is the span of a set. In the previous discussion of what it meant for vectors to span a space, there we were kind of using span as a verb. Something that vectors do. They span a space, they cover a space. So we want to say, for this first part of this example, find a vector h in the span of vectors f and g, where f of x equals 2x squared plus x, and g of x equals 3x minus 1. Well, a vector h in the span of two other vectors really just is a vector that is a linear combination of these two f and g vectors. So really any linear combination of f and g will give us an h that's in the span of fg. So let's write this down. For example, maybe we let h of x equal, let's even say it this way, maybe we let function h equal, I don't know, 2 copies of f minus a copy of g. That's a linear combination of f and g, so that'll work. And all that really means is that h of x is 2 times what f of x equals minus a single copy of what g equals. And if we simplify that down, 4x squared minus x plus 1. So we could say h of x the way we've defined it is one vector in the span of fg. Right? So that's not too bad. In the next one, we're just asking a similar sort of question. Instead of saying find a vector in the span, here we're saying here is a vector. We're calling it j. Is this vector j in the span of fg? I'm emphasizing to call these things vectors. Even though they're really polynomials, I'm calling them vectors because we're really thinking of this vector space sort of view of these things. But if we want to see if j of x is in the span of fg, what do we have to do? We just have to find or determine whether we can find a linear combination of f and g that gives us j. If so, j by definition is in this span. It's a linear combination of f and g. So we set this up. J equals c1f plus c2g, which really just, remember, means j evaluated at any x has to be c1 times f of x plus c2 times g of x. Well, let's go ahead and replace this j of x over here with what j of x equals. It's x squared plus 2x plus 1. So let's put that here. Let's make that little deletion and change this up. And we solved this the same way we solved the linear combination involving functions earlier. We just equate coefficients of like powers of x on both sides of the equation. So for the x squared coefficients, we would get 1 on the left side equals 2c1 on the right side. That's it. For the single powers of x, we get 2 is the coefficient of the single power of x on the left side. So it looks like c1 plus 3c2 is going to be what we get on the right side. Finally, the 0 powers of x, or the constants, these would give us 1 on the left. And it looks like just negative c2 on the right. But here we have it, yet again, system of linear equations where the unknowns are those scalars c1 and c2. So if we want to solve this, I probably wouldn't even pack this up into a matrix. I'd just solve this individually. This guy tells us c1 has to be a half. This guy tells us c2 is -1. But if you check it, I don't think these values, c1 and c2, I don't think these values actually satisfy the second equation we had here. All right, so let's write 2 does not equal the c1 value plus 3 times the c2 value, which would be -3 plus a half, -2.5, or 5/2. Right. So this shows we cannot write J as a linear combination of f and g, therefore it's not in the span of f and g. Oops. J is not in, that's my J, span of FG. Right. That's it for this section. The next videos will be for 4.3, where we talk a little bit more about similar ideas, but with linear independence in mind.